Take a slow breath. That oxygen has a long way to travel from the air in this room all the way down to the tiny engines inside your cells. And at every step along the way, its pressure drops, like water falling down a set of stairs. So let's follow it down those stairs together, and then let's meet the molecule that carries it. This staircase has a name, the oxygen cascade. We measure oxygen by its pressure in units called kilopascals. Dry air starts high at about 21. As you breathe in, your airway warms it and wets it. Water vapor takes up some of the room, so it slips to around 20. Down in the air sacs of the lungs, carbon dioxide is always leaving the blood and filling that space, so oxygen falls further to about 13. It crosses into the blood with only a small step down. Out in the tissues, it's near 5. And inside the cell's engines, the mitochondria, it's just 1 to 3. Every step is a little drop. The whole staircase, that is the cascade. The biggest step down is getting into the air sacs, the alveoli. Why such a big fall? 2 reasons. First, the water vapor we just added. It takes up space. Second, carbon dioxide. It is always streaming in from the blood, and it takes its share of the room too. There is a simple sum for the best oxygen an alveolus can reach. It is called the alveolar gas equation. Don't worry about the maths. Hold on to the idea. Breathing in adds oxygen. Carbon dioxide takes some away. On room air, the answer lands at about 13 kilopascals, 100 in the older units. Now, put 2 numbers side by side. The oxygen inside the air sac and the oxygen that actually makes it into the artery. In a perfect lung, these 2 would be equal. In real life, the artery sits just a little lower. That small difference has a name, the AA gap. It is a quick measure of how well the lung is doing its job. In a young, healthy person, the gap is tiny. It grows a little with age, and it grows when the lung is unwell. So, oxygen is now in the blood. But how does it actually travel? In 2 ways. A very small amount simply dissolves in the watery part of the blood, the plasma, really small, only about 1.5%. Almost all of it rides on a carrier called hemoglobin. Picture hemoglobin as a little bus with 4 seats for oxygen. Each gram of it carries about 1 1/3 milliliters. Fill the buses, and the blood is loaded. So whenever we talk about oxygen in the blood, we are really talking about hemoglobin. Now let's draw a picture of hemoglobin filling up. Down the side, we put how full it is, its saturation. Along the bottom, the oxygen pressure pushing in. You might expect a straight line, but it isn't straight. Here is the trick. As the first oxygen climbs aboard, it changes the shape of hemoglobin and makes the next seat easier to fill. The seats help each other. We call that cooperative binding. And that teamwork bends the line into an S. This S has a name, the Oxyhaemoglobin dissociation curve. 3 points on this curve are worth keeping. The middle, where hemoglobin is exactly half full, sits at about 3.5 kilopascals. We call that the P50, the curve's name tag. Higher up at 8 kilopascals, hemoglobin is 90% full, and the blood returning from the body, the venous side, sits around 5, about 75% full. Half full, 90%, 75%, 3 dots that pin down the whole curve. Now look at the shape, because the shape tells a story. The top of the curve is flat. Up here, pushing the oxygen pressure even higher barely adds anything. The buses are already nearly full. That flat top is a safety margin. Even if the pressure dips a little, the saturation holds. But lower down, the curve turns into a cliff. Here, a small drop in pressure causes a big fall in saturation. That is why a saturation of 90% is the edge of the cliff, and why we get worried the moment it starts to slide. The curve can also slide sideways. Picture a hard-working muscle. It is warm, it is acidic, it is full of carbon dioxide. Every one of those pushes the curve to the right. A right shift means hemoglobin loosens its grip and hands oxygen over exactly where the busy tissue needs it most. There's one word to remember the causes: cadet. Carbon dioxide, acid, DPG, exercise, temperature. Right shift means unload. The opposite move is a left shift. Cold tissue, low acid, stored bank blood, fetal hemoglobin, these slide the curve to the left. Now, hemoglobin holds on tighter and gives oxygen up less easily out of the tissues. Carbon monoxide is the dangerous one. It does 2 bad things at once. It steals the seats and it drags the curve to the left. So the little oxygen left on board is held even tighter. Left shift means hold on. One last idea, and it is the one that matters most at the bedside. What truly reaches the tissues is not the oxygen pressure. It is the delivery. And delivery is just two things multiplied together: how much blood the heart pumps each minute and how much oxygen each portion of blood carries. That carried amount is almost all hemoglobin. So the big levers are hemoglobin in the heart, not the oxygen pressure. Always look at the whole picture. So here is the whole map in 4 pictures. The cascade, pressure falls step by step from the air all the way to the cell. The curve, an S, flat and safe across the top, steep and dangerous at the bottom. The shifts, slide right to unload at busy tissues, slide left to hold on, and delivery, the heart multiplied by the hemoglobin. Get those 4, and oxygen makes sense.